Hello guys, my name is Shishir C. I'm from Sri Venkateswara College of Engineering. My USN number is 1VE23CS157. Today we are going to learn about a maths topic, vector space and subspaces. What is a vector space and subspaces? The definition of a vector space is a non-empty set of vectors of objects called as vectors, which are defined to operate called as additions and multiplications by scalar subject to the 10th axioms listed below in listed below. The axiom must hold for all vectors u, v and w in v and for all scalars and c and t. The sum of u and v denotes by u plus v is in v. U plus v is equal to v plus u. U plus v plus w is equal to u plus bracket open v plus w bracket close. For each u in v, there is a vector u in v such that u is equal to v u is equal to bracket open minus u bracket close minus 0. The multiple of u by c denoted by cu is in v, where c bracket open u plus v is equal to cu plus vc, and the second formula is c plus d bracket close u is equal to cu plus cd. This is a simple multiplicative um, formula, and this is a constant. L is constant over here, and u is equal to u constant into u is equal to u. Subspaces in vectors. What is a subspace in vectors? A subspace is a subset of a vector space that is also a vector space, where there's already a vector space at the first, but there's another vector space inside a vector space which is also a vector space, is known as subspace vectors. This means that a subspace is closed under addition and scalar multiplication. Basically, in subspaces acts as a vector space also. Basically, you can multiply and add to scalar quantities in the vector and conducts the zero vector. A subspace is defined relative to its constant space. It already means subspace is defined as relative to its containing spaces and can have a lower dimension than the containing space. It should have a lower dimension because it is already a subspace of a vector. It has a lower dimension. Vector space is more greater space than a subspace. So basically, it has lower dimensions than the containing space. A vector space is a subspace of itself. Okay, a vector space is a subspace of itself, and the zero vector is a subspace of every vector space. There are many types of vector. Null vector. Basically, null vector is also known as zero vector, and zero vector is a subspace of every vector space. Subspaces. Okay, we are again talking about subspaces. Given a vector space V over a field K, there's a vector space V over a field K, the span of a set of S of vectors, not necessarily finite, it can be infinite also, uh, is defined to be the intersections W of all subspaces of V that contains S. W is referred as subspace spanned by S or the vectors in S. Well, once again, we'll understand and read. There's a given vector in the space V over a field K. K is a field and there is a vector V inside the scale. The span of the sets the span of a set of S vectors. There is a span of many vectors, necessarily not finite, is defined to be the intersections W of all spaces of V that contains S. A subspace of a vector is subset of vector also of satisfying. A non-emptiness, the zero vector, is in vector V. Closure under addition. If vector u and vector v are in vector space, then vector u plus vector v is also known as vector v. Okay, there are two vectors. And there is a simple addition going on over here. Closure vector under scalar multiplication. If vector v is in the vector and the vector c is in vector r, then cv is also known as a new vector. If V spans over V2 and VP are continuous over here, the span, we say that V is also a subspace. V is also a subspace. One second. Here V is also a subspace by generated by the vectors. Any matrix naturally gives the rise to of two vector space. Let A be the common as vector. We can multiply vectors as in the form of matrix also. The common space of the subspace is spanned by the columns A, and then null space is represented by consisting of some solutions of homogeneous equation. A is equal to 0 and B vector is also equal to 0. The column space and the null space of a matrix are both subspaces so that they are both spanned in the column spaces of a matrix A. Is defined to be a span of the columns of A. The null space is defined to be the solution of set of AX is equal to 0. So this is a good example of kind subspaces that we can define without any spanning set in mind. In other words, it is easier to show that the null space is an subspace than to show it's a span of see the proof above. In order to where's the proof? Okay, this is the proof of subspaces and columns, and this is the definition. Writing a subspace of as a column space or a null space. A subspace can be given to you in many different forms. In a practice computation involving subspaces are much easier if you are a subspace in column space or null space of a matrix. The simplest example of such computation is finding a spanning set or column space is by definition the space of the column of matrix, and we show the above how to compute a spanning set of all these null set using parametric vector form. This reason is useful to rewrite a subspace in a column space or null spaces before trying any answering question about it. This is the example, you can note it down. Null space is equal to span is equal to 0. This is very important. This is a natural definition of span. S span span is equal to null space, which is null is equal to 0. A is equal to 1, 2, 3. Solution. We compute the parametric vectors from the form of A is equal to x. Okay, we A is equal to x in form. Okay, you have to just study about it. And thank you for watching my video. Please like, share and subscribe. We'll meet you in the next video.